This chart illustrates a standard ordinary least squares regression trying to fit a binary outcome, like a pass or fail. Because classical regression is rigid, the straight prediction line quickly overshoots reality, generating impossible probabilities that drop below 0 and rise above 1. These classical techniques, formalized by Gauss and Legendre, were originally built to measure continuous quantities, where errors in measurement naturally maintained a constant variance. But as statistics expanded into biology and agriculture, researchers needed to track discrete events, like the exact number of infected crops in a grid or patient recovery counts. Because linear regression couldn't handle this non-normal data, statisticians built isolated, bespoke mathematical methods to fill the gaps. To handle the volatility of real-world data, we must move past the assumption of constant variance and Gaussian error. Linear regression, logit models, and log linear models are not separate techniques. They are special cases of a single mathematical class, the generalized linear model. A GLM breaks statistical modeling down into three distinct modular components: a probability distribution, a linear predictor, and a link function. This architecture operates under one strict constraint. It assumes every observation in your dataset is independent. By separating these three functions, you can apply the computational efficiency of linear equations to almost any dataset you observe. The first rule of a GLM is that the probability distribution of your data must belong to the exponential family. This equation represents the exponential family density function, the universal template. Inside, theta is the natural parameter, derived from the mean. Phi acts as the scale parameter. By swapping these, this single equation generates the normal, Poisson, or binomial distributions on demand. Notice the function b of theta inside the template. In this architecture, that single function dictates both the expected mean and the variance of your data. Because variance is a direct function of the mean, the GLM natively adapts to shifting variance in discrete data, providing stability where classical regression fails. The second pillar is the linear predictor, represented by the Greek letter eta. This component acts as the central hub for your measurable effects. It operates exactly like classical regression, calculating a value based on your specific covariance. It incorporates continuous quantitative data, mapping inputs like an individual's age or the duration of a trial. It simultaneously processes categorical factors. If you introduce sex or distinct medical treatment groups, the predictor assigns a specific mathematical weight to each category level. It also accounts for interaction effects, where the mathematical impact of one variable scales based on the presence of another. No matter how many variables or layered interactions you record in the real world, the linear predictor compresses them into a single combined numerical value. But here we hit a mathematical conflict. The linear predictor can output any number from negative to positive infinity. The actual expected value of your data, however, often has natural boundaries, like a percentage, which cannot drop below 0. We bridge that gap with the link function. It serves as the translation layer, connecting the bounded mean of the real-world data to the unbounded output of the linear predictor. An actuarial model predicting exam success tracks tutorial attendance, 3 assignments, and a 65% mock score. The predictor outputs 1.7682. This impossible probability is pushed through the inverse logit link function, compressing it to 0.8542, an 85.4% chance of passing. The link function is the critical safeguard of the system, ensuring the GLM always outputs logically sound predictions, regardless of the data's native constraints. If classical error metrics, like the residual sum of squares, are invalid for these non-normal distributions, we need a new way to verify the accuracy of the model. We evaluate fit using likelihood, pioneered by R.A. Fisher. This metric measures how plausibly a specific mathematical model explains the observed data. For a GLM, the universal fit metric is called deviance. To calculate it, we compare the log likelihood of our working model against a theoretical saturated model, one that assigns a unique parameter to every single data point to achieve a perfect fit. This table tracks insurance deviance across policyholder age, vehicle age, and car group. By adding the car group factor to the age model, we sacrifice 3 degrees of freedom, but scaled deviance drops by 226.5, proving the added complexity significantly improves accuracy. There is a strict constraint to this test. Deviance comparisons are only mathematically valid for nested models that share the exact same distribution and link function. Deviance provides a mathematical check against overparameterization, allowing us to balance predictive precision against the structural complexity of the model. The GLM pipeline is highly structural. Chaotic data is mapped to an exponential distribution. Real-world variables are compressed into the linear predictor. The two are bridged by the link function, and the final output is tested via deviance. By separating the native distribution of the data from the linear mathematics predicting it, statisticians retain the speed of classical computation without sacrificing accuracy. This architecture provides a singular framework that brings mathematical order to the nonlinear and non-Gaussian patterns of the natural world.